This is the first of several lessons in sound waves in the simple harmonic motion and waves unit. To review waves, we know that they carry energy from one point to another, that they have a speed, and there are different types. And waves can be a pulse, but typically they exhibit simple harmonic motion, and so we see them have common properties such as period, frequency, etc. A wave is a disturbance that propagates from where it was created. And when we think about sound waves, that's exactly what the model is that it's a disturbance of matter. Notice specifically here that sound needs a medium. It needs matter. It cannot exist in a vacuum like another wave can. So it's a disturbance of matter created by a vibrating object, so we're going to see simple harmonic motion, that is transmitted from its source outward radially. And that's true for all waves, but let's focus on the vibrating object part. I put a guitar string over here. You can see that the string is vibrating back and forth, and what happens is this creates pressure waves. Here's a tuning fork, and you can see pressure waves through these media. This is air, and I put the pressure graph over here for noise versus music. And I know what you're thinking, some music may be classified as noise. But the main difference is that music is created by a vibrating object. Sound is created by a vibrating object, right? We have vibrating here. Some noises aren't created by a vibrating object. You may just hit the table, and that's a slap, and that's a noise, right? But it wasn't created by a vibrating object. Sound is pressure waves moving through a medium. So it needs a medium to exist. They are longitudinal. This pressure vibrates in the direction of the wave. So if the wave moves in this direction, you can see that the particles will vibrate back and forth in that one spot. And the pressure between them gets larger and then gets less. And that's what we call compressed or rarefied, is when it's greater or less. Just like every wave, sound has a speed, and it's the same equation as it is for all waves. The speed of the wave is related to the wavelength and the frequency. Remember, the wavelength is the distance between successive crests or successive troughs, and the frequency is how many cycles happens in 1 second. This is measured in hertz. As mentioned before, sound needs a medium to travel, and thus the speed of sound varies depending on the medium. And I put a couple of charts here to reference from OpenStax and Cutnell and Johnson. And you can see that they arrange them from gases to liquids to solids and also different temperatures. For instance, air at 0 degrees, it's 331 meters per second, and air at 20 degrees is 343 meters per second. So you can reference these charts to see how fast sound travels in the different mediums. If there is a conflict, so seawater, I notice the difference between seawater at 20 degrees Celsius is different here. I would reference Cutnell and Johnson's chart here. You can always look on the internet and find these out. With the properties of sound laid out, which is just a few of them, it's very simple, we're going to do some problems to get you used to thinking about sound waves and doing some problems on sound waves. The first is name that substance. It says, what is the speed of sound in a medium where 100 kilohertz frequency produces a 6 centimeter wavelength? Which substance is this likely to be? So when I read this, I see that there's a hertz, which is a frequency, and I'm going to write this in hertz instead of kilohertz. A kilo is 10 to the third, so that's hertz or 1 over seconds. The wavelength, they say, is 6 centimeters, but I'm going to convert that to SI, which is 0.06 meters. I know the velocity of the wave, I put that on a slide a little bit earlier, is the wavelength times the frequency, so I can take those two numbers and simply multiply them together. So I have 100 times 10 to the third times 0.06 meters, and when I multiply those together, I get 6,000 meters per second. So that's pretty easy, straightforward, and it's the same equation you know and love for waves. This is true for all waves, which include sound waves. When I look at this chart, so that was like the first question, what was the speed of sound? It says, which substance is this likely to be? So when I look back at the chart, I look at the highest, it looks like it may be steel. You see that there's 5960. So a pretty solid substance with a very fast speed of sound in there. And what I will note here is that the frequency is very fast frequency, very fast. And also the wavelength is pretty every day, like 6 centimeters is like that. So in steel, you can imagine maybe a steel beam and yelling at the end of it maybe to get sound moving through it. And the sound moving through that will be 100 kilohertz at 6 centimeters of amplitude. So you can imagine that, a steel beam. Hopefully you're getting a picture in your head of sound waves. This next problem should help you as well, where I have sound in two mediums. It says dolphins make sounds in air and water. What is the ratio of wavelength of a sound in seawater to its wavelength in air? Assume a temperature of 20 degrees Celsius. Okay, so if you look back at the chart, and at the 20 degrees Celsius, I see that we want the speed of sound in air and the speed of sound in water. So the speed of sound in air is going to be 343 meters per second at 20 degrees Celsius. The speed in water is going to be in seawater. I'm going to go with Cutnell and Johnson's 1522 meters per second. It probably depends on density of the salt, the salinity of the water, etc. But we'll just use that value and say the dolphin is in that water. What is the ratio of wavelength? So I know the speed is related to the wavelength like this. So I'm going to solve this equation for wavelength. So I get velocity over frequency. I can do this for each medium. The wavelength in air is going to be the speed in air over the frequency in air. And the wavelength in water is going to be the velocity in water over the frequency in water. What I'm going to note here, it says a sound. And what distinguishes a sound is its frequency, right? We have a vibrating object, and that will determine its frequency. So when I look at a sound, one sound has one frequency, so we're going to say that the frequency in air is the frequency in water. Keep this property in mind as you head towards learning about light and light waves. When light enters a medium, the frequency stays the same. It's the wavelength that changes, and that's the same with sound. The wavelength will change, not the frequency with waves. So FA equals FW. I can kind of eliminate those subscripts so that there's just one frequency. So let's do the ratio of the wavelength of seawater to air. So we want to put lambda water over lambda air. I'm going to put V water over the frequency over V air over the frequency. You can see that the frequency cancels on the top and bottom to unity, and we get the velocity of water over the velocity of air will equal the ratio of the wavelength of water over the wavelength of air. I'm going to plug those numbers in. We have 1522 over 343. When you run that through the calculator, we can see that the wavelength in water will be much larger than the wavelength in air. This number actually comes out to 4.43732. I held some sig figs, but about 4.4. What I am going to draw for you so you get an idea, and we're going to keep in mind that these two waves have the same frequency. It's one sound, it has the same frequency. It's the wavelengths that change. So when I look at the wavelength in water, it's pretty long, okay? So I'll draw a long wavelength wave. So there's 3 crests. I can do the same thing for the wavelength in air, and it's going to be about 4.4 times shorter, right? So I'm going to go like this. And ideally, these would have the same amplitude, but I'm not worried about that artistically right now. What I want you to imagine is these two waves traveling in space. And notice that they have the same frequency, so they are going to peak at the same time, and they are going to trough at the same time. but the top one will travel much farther in the time it takes for it to peak and then trough again than in air. And that gives tribute to the distance between the molecules. The molecules in water are much closer together. They're going to feel that their neighbor press against them and feel that pressure much quicker, and it will travel much faster in a denser material than it will in air. It'll travel slower in air. This reminds me of how they used to tell when trains were coming. They wouldn't listen to the train, they would listen to the train track, the actual tracks of the train, that the sound traveled down those tracks faster than it did in the air, and they knew when the train was arriving. I've chosen one more problem for us to look at, and it's a frequent one you'll see in problems about echolocation. This may be dolphins. You saw in a previous problem we talked about dolphins. It could be something in the air, a submarine, a boat, bats, echolocation. Bats use echolocation. So you'll see this application frequency. So I wanted to cover this so you were thinking about the factors that go into echolocation. It says a sonar echo returns to a submarine 1.23 seconds after being emitted. What is the distance to the object creating the echo? So here's the submarine here, and it lets out a sound wave, and it goes and it hits the object, and then it reflects back. Okay, so the distance that this wave travels is 2d, whatever it is, d, which is what we're asked to find in the problem. What is the distance to the object? So we want to find d. We don't know what d is. And notice that the 1.2 seconds is the time for it to go there and come back again. So the time for one trip, or one distance d, is going to be the time for the whole trip divided by 2, which is 1.23 divided by 2. And that's 0.615 seconds. You can calculate it if you like, or hold on to that value. What we want to find is the distance. Well, the distance, I know, is for a constant speed. Distance is related by constant speed and time with the velocity. So distance has to equal velocity times time. Assume that the submarine is in the ocean with a speed of 1,522 meters, not fresh water. There's a difference there. So if we're in the ocean, we want to use 1522, and the time is 0.615, and the distance to that object away from the submarine is 936 meters. I'm highlighting this problem because you will see a problem in your homework where there's a couple of different mediums, and remember, you have to take that and multiply. If it's sonar, if it's echolocation, you have to remember that factor of 2 in the problem.